Today, we're diving into something, well, really fundamental if you're working with structured information. We're talking about the essential building blocks of using databases with SQL. We've got your notes and excerpts right here, quite a stack actually, focused squarely on the most basic SQL operations and some great practice ideas to our mission. Let's unpack this stuff for you, pull out the really crucial concepts, and try to make them super clear, actionable, maybe even a little bit interesting. Think of it like getting a clear map to start finding your way around the world of databases.
That's a great way to put it. SQL, structured query language, it really is the standard language for managing and manipulating relational databases. And honestly, understanding these basic commands, it isn't just for DBAs anymore. It's pretty essential for anyone interacting with data. You know, whether you're building apps, analyzing information, or even just trying to get a handle on how data's stored and retrieved in so many systems you use every day. So yeah, we'll walk through the core steps from these sources, starting with setting up your environment, defining the structure, then moving into actually working with the data, adding it, changing it, pulling out exactly what you need.
Okay, sounds like a plan. Let's unpack this. Ready to dive into the absolute basics of SQL. All right, let's start at the very, very beginning. First things first. Before you can put any data anywhere, you need the actual place to put it. So that first step in the source material is creating the database itself. The command is create database. Pretty self-explanatory, right? It creates a new database instance. The structure looks like create database, database name. Simple as that. And the notes give us a nice clean example. Create database company data. That one line sets up a whole new sort of separate space for your company's info.
Right. And the why here is important. It's kind of like getting a brand new filing cabinet before you start making folders and stuffing papers in. It gives you that distinct environment for related tables and data for a project or an application. Keeps things organized.
Okay, that makes sense. So you've got your filing cabinets, your databases. Now you need a way to say, okay, I want to work inside this specific cabinet right now. And that's where use database comes in, according to the notes. It selects which database becomes your current working one. It's just UC database name. So following the example, after you create company data, you probably run UUC company data right away.
Exactly.
And then any commands after that, like making a table, apply to company data.
Precisely. It gives the system context. Without it, the database wouldn't know where you intend to, say, create your next table or insert data. It's simple, but absolutely necessary.
Got it. Okay. Database selected. We're in the right cabinet. And now it's time to define the structure inside that cabinet, the blueprints for your information, the tables. And the command for that is create table. Defines a new table, you give it a name, and then inside parentheses, you lay out all the columns it's going to have. You specify what kind of data goes where, set up rules. The basic structure is create table name. And inside those parentheses, that's where the details are, defining each column. What kind of info can it hold? The source notes list the common data types, int for whole numbers, varchar for text where the length varies. We set a max. Chuhar for fixed length text, decimal for exact numbers with decimal places.
Right, like currency, you specify the total digits and how many are after the decimal.
Yeah, and then date time, and Boolean or Teni Intai type one for true false values. So the data type dictates what you can actually store in there.
And then you layer on top of that the constraints. These are the rules. Really important. They're not suggestions. The database actually enforces them to keep data reliable. The source lists some key ones. Primary key. That's your unique identifier for each row. No duplicates, no blanks, no NLs.
Like an employee ID number.
Exactly. Then there's auto increment. Often goes with the primary key. Automatically generates the next number in sequence. Super handy for IDs. Not NL just means this column has to have a value. Can't leave it empty. Unique ensures all values in this specific column are different from each other. Default lets you set a value that's used automatically if you don't provide one when inserting data. Foreign key, this is a big one for relationships. It links this table to another table, ensuring data here matches a valid entry over there.
Connecting the dots between tables.
Precisely. And cheat code lets you define a custom rule, like making sure a number is positive or a value is within a specific range.
Wow, okay. So create table is much more than just naming columns. You're really designing how the data has to behave.
You nailed it. It's the blueprint and the house rules. The source material uses that employee's table example really well. Let's look at that definition. Create table employees. 8AT. Primary key auto increment. C. Integer, it's the primary key, so it's unique, and it auto increments. That's the employee ID sorted. Name varchar 100. Text for the name up to 100 characters long. Department varchar 50. Text for the department max 50 characters. Salary decimal 10 2 in the salary field. Decimal 10 2 means it can hold up to 10 digits total, with 2 of those digits after the decimal point. perfect for money, keeps it precise. Huh. So running that command, it sets up that exact structure with those rules inside your company database, ready to hold employee records.
Okay, the blueprint is ready, the structure is built. Now, how do you actually put the data in? The employee records, the product details, whatever it is, and then how do you work with it? This sounds like where data manipulation language, DML, comes in, commands for the data itself.
That's right, DML.
First up, getting data into the table. Insert. This adds new rows, new records. You can specify exactly which columns get which values, or if you provide a value for every single column in order, there's a slightly shorter way. The notes give us these examples for our employees table. Insert into employees, name, department, salary, values, John Doe, IT 50,000. This seems clear. Put these values into these specific named columns. We didn't list EAD.
Because it's auto increment. The database handles it.
Right. And the second example, insert into employees' values. NULL, Jane Smith, HR 60,000. This gives values for all columns, but why NULL for the ED here?
Good question. Because EAD is auto increment, the database assigns the next unique number itself. By putting an LL there, you're essentially telling the database, you handle the ID, I'm not providing one. It triggers the auto increment mechanism.
Okay, got it. So NL here means let the database figure it out.
Yep. And insert is how you populate your tables day to day, adding new users, new orders, new products, everything.
Makes sense. Data's in. Now, how do you see it again? How do you get it back out to look at or use in an application or analyze? This must be the most common one. Select.
Oh, absolutely. Select is your workhorse.
It retrieves data. The basic form lets like select columns from table name where condition, and you specify which columns you want by listing their names, like name, salary, or you can just use to mean give me everything, all columns.
Exactly. And that where clause, that's where the real power comes in for filtering. It lets you specify which rows you actually want back. So select from employees gives you the whole lot, every column, every row.
Probably too much sometimes.
Often, yeah. Then select name, salary from employees, much more focused, just names and salaries. Select name, salary from employees where department IT, now we're filtering. Only show name and salary for rows of the department column is exactly IT. Or select name, department from employees where salary 52,000, filter based on a number. Show names departments only for employees earning more than 52,000.
So where is how you ask specific questions? Not just show me employees, but show me these specific employees.
Precisely. It turns a big pile of data into a targeted answer. Hugely important.
Okay, so data in with insert, data out with select. What if something changes? Someone gets a raise, moves department, updates an email address. You need to modify existing data. And that's the job of update, right? It modifies rows that are already there. It's like update table name set, column 1 equals value 1, column 2 equals value 2, where condition.
Yep. And again, the examples from the source are spot on. Update employees set salary 85,000, where name H.A. Doe, changes just John Doe's salary. Notice the where clause makes it specific to him.
Right. Targets one person.
Update employees set salary 1.10, where department equals his HR. This one's interesting. It performs a calculation. Increases salary by 10%.
Oh, neat. You can do math right in the set clause.
You can, but only for employees, where the department is HR. Again, where limits the scope.
Yeah.
And update employees. Set department, marketing, salary equals 62,000, where it equals 3. Shows you can update multiple columns at once for a single row, identified here by its unique id.
Now, the source has a big warning here about update. It sounds like a classic mistake you could make if you forget the where.
Oh, absolutely. This is critical. If you write an update statement and you forget the where clause.
Which just updates
It updates every single row in the table with the values you specified in set. Imagine accidentally setting everyone's salary to 50K or everyone's department to sales. Disaster.
Yikes. Okay. Always double check the where clause with update.
Always.
All right. Final core operation, getting rid of data. Sometimes records just need to be removed. For that, the command is delete. Removes rows. Syntax is delete from table name where condition.
Following the pattern, the examples show. Delete from employees where name John Doe. Removes the row, or rows if names weren't unique for John Doe. Delete from employees where department finance. Removes all employees in the finance department based on that condition. And delete from employees. Just like update, what happens if you omit the where clause?
Oh no, it deletes everything.
Every single row in the table. Gone.
Wow. So the same warning applies, maybe even more strongly because deleting is usually permanent.
Exactly. Delete removes the data, the rows. The table structure itself remains empty. The source notes also mention drop table.
Ah, yeah, that's different.
Very different. Drop table removes the entire table structure and all. The blueprint itself is gone. But yes, forgetting where on a delete is incredibly dangerous. Backups are your friend.
Okay, message received loud and clear on where clauses for update and delete. So we've covered the essentials. Create database, use, create table for setup, then insert, select, update, delete for working with the data. The source material then gives us some great pointers for going a bit further, connecting related information between tables and summarizing data. The practice ideas revisit create table by suggesting tables for things like projects or departments or students. And looking at those, you see the same concepts, different data types like date, more constraints like check for GPA rules, unique for project names, not null, etc.
And what really stands out there is a practical application of the foreign key constraint. That's how you formally link these tables. The projects table example links to departments. And the source even gives a detailed walkthrough of modifying our employees table, adding a departmented column.
Right, instead of the department name text.
Exactly, making that department in a foreign key that references the id in a new departments table. It shows using alter table to add the column, ubate to populate it, and drop column to remove the old text-based one.
So that foreign key enforces the relationship. It ensures an employee's departmented actually matches a real department in the department's table.
Precisely. It guarantees the link is valid. No orphan employees assigned to non-existent department IDs. It's fundamental for relational integrity. Now, once you have these linked tables, how do you pull data that spans across them? Like seeing employee names and their full department names together.
That sounds like the job for joins.
You got it. Joins combine rows from two or more tables based on a related column, typically the primary key in one table matching the foreign key in the other. The source highlights a couple of key types. First, inner join. Inner join returns only the rows where there's a match found in both tables based on your joining condition. If an employee has a departmented that doesn't exist in the departments table, that employee simply won't appear in the results of an inner join.
Okay, so inner join is for when you only want records that have a definite link in both tables.
Correct. Then there's left join, sometimes called left outer join. This one returns all rows from the left table, the first one listed after from, and then the matching rows from the right table. Crucially, if a row from the left table doesn't have a match in the right table, it still appears in the result, but the columns from the right table will just show up as an LL for that row.
Ah, okay. So left join is what you'd use if you wanted to see every employee, even if maybe their department details haven't been properly linked yet. You'd see the employee info and just NLLs for the department name.
Exactly right. It lets you see everything from one side of the relationship and pull in related details if they exist. Very useful for seeing the complete picture from one table's perspective.
Got it. Different joins for different questions. The source also covers ways to crunch the numbers, basically, to summarize and organize data for reports or analysis, not just pulling raw records. This is where group by, having, and order by come into the picture.
Okay, group by why? This clause groups rows that have the same values in one or more columns into a summary row. It's almost always used with aggregate functions like count, AVG, average, SUM, MIN, max. The example was counting employees per department, select department, count from employees group by department. It collapses all the individual IT rows into one summary row for IT showing the count, same for HR, etc.
So it summarizes based on shared values.
Exactly. Then having filters the results of a group by. It filters the groups themselves. The example, finding departments where the average salary is over $52,000. Having AVG salary $52,000. You use having here because you're filtering based on the result of the aggregate function, AVG salary, which only exists after the grouping has happened.
Right. You couldn't use where for that because where filters individual rows before they get grouped.
Perfect. Where filters rows, having filters groups. That's the key difference. And finally, order by. This one's pretty straightforward, but essential for presentation. It sorts your final result set. You can sort by one or more columns, ascending ASC, which is usually the default, or descending DESC. The example showed sorting by salary, high to low, by name alphabetically for ties. Order by salary, DSC, name ASCS. Just makes the output neat and organized.
Okay, so using group by, having, and order by together lets you turn potentially messy raw data into really meaningful summaries and nicely sorted lists. The source also briefly mentioned things like stored procedures or views as ways to sort of package up complex SQL or create reusable virtual tables. It referenced a get employees by department store procedure as an example.
Yeah, those are ways to save and reuse common or complex queries, make things more modular. Good concepts for later, but built on the foundations we've discussed. So we've really covered a lot of ground. Setting up with create database, use, create table, understanding those crucial constraints like primary key, foreign key, then manipulating data with insert, select, update, delete, and hammering home the importance of that where clause. And finally, touching on connecting data with joins and summarizing with group by, having, and order by.
These really do feel like the absolute core tools for talking to relational databases. Getting comfortable with these commands, it feels like it unlocks a huge amount of power for managing and just understanding data.
It really does. And remember, the source material you have includes specific practice examples. Honestly, the best way to make this stick: get hands-on, open up a database tool, try creating tables, inserting data, running those selects and updates, make mistakes. That's how you learn. See how the data changes.
So what's the big takeaway here? Fundamentally, these basic commands let you build structured storage for information and then perform pretty much any operation you need on that data, querying it, changing it, managing it reliably.
Which leads to an interesting thought. As you start thinking about creating tables, defining those relationships with foreign keys, setting rules with constraints right from the start, consider this. How does the initial structure you design, the way you set up your tables and columns and links, how does that directly influence the kind of questions you can easily and efficiently ask later using select, join, and group by why?
So the design up front impacts the analysis you can do later. Definitely something to ponder as you continue learning SQL.